Greetings! Welcome to Electronic Circuits 1. This is lecture number 10, and I am Razavi. Today we will look at two circuits using diodes. These circuits are used in many applications. One is called a half-wave rectifier, and the other one, the full-wave rectifier. Last time we briefly talked about the half-wave rectifier, and I would like to refresh your memory about what we covered and now how we will continue. So, last time we said that in addition to looking at IV and input-output characteristics of circuits, we are also interested in one more type of behavior, namely the time response. Now, of course, we know time response from electric circuit theory courses, but here we also would like to apply some sort of input wave, maybe a sinusoidal wave, to the circuit, and then see what comes out of it. This is ultimately what really the circuit does. The input-output characteristic and the IV characteristic are only for our own understanding and our own insight, but the actual behavior of the circuit is its response to a time domain waveform. Now, we said that a half-wave rectifier is simply a diode D1 and a resistor R1. It behaves like so. First, we looked at the input-output characteristic, and we saw that if the input voltage is negative, D1 is off, there's no current through D1, there's no current through R1, and the output voltage is 0. So the output voltage was 0 up to a certain value of the input. How much voltage do we need to turn on the diode? Well, one diode drop, VD on, if we use the constant voltage model. So at VD on, the diode turns on, and from here on, the input just goes to the output with a slope of 1, and the only difference is that the output has a level shift with respect to the input. If the input is 2 volts, the output is 2 volts minus VD on. This was an important property. We said that the output is pinned to the input, meaning that as the input changes, the output also changes in proportion, except that there's a shift of VD on between the two. We said the output tracks the input, or the output is pinned to the input. All right. Now, we said, okay, let's, in addition to looking at the input-output characteristic, let's look at the time response when the input is a sinusoid. So we have a sine waveform coming in, shown here in black, and we would like to see what happens at the output of the half-wave rectifier? Well, we said that if the input is small, near 0, then the diode is off and nothing happens. This output is 0. So the output is 0. When the input is large enough, one diode drop, VD on, then the diode turns on and the output is pinned to the input, meaning that the output tracks the input. So if the input is going up, the output also goes up. The difference being one diode drop, VD on. And then this continues until the input comes back down enough to turn off the diode. And that again happens when the input is equal to one diode drop. So at that point, the diode turns off, the current is 0. Now, if the input comes down further and then goes and becomes negative, the diode remains off, there's no current, the output remains at 0. So the output remains at 0. And as this input waveform repeats, so does this output waveform. And that's the waveform that we get. Okay, this is what we call a half-wave rectifier. Rectifier because it passes, for example, positive cycles of the input, and half-wave because it only passes these half cycles. It doesn't pass the other half cycle. Now that may seem redundant. It seems that every rectifier has to be half-wave rectifier, but we will see shortly that that's not exactly true. Okay, so this is the type of waveform that a half-wave rectifier produces. And now we would like to analyze this a little further and understand what it does, then try to add a capacitor at the output. We will see why. And that has some interesting implications. And once we are done with that, we're comfortable with analyzing that circuit, we go to a more complete and interesting circuit called the full-wave rectifier and perform all those analyses again for this one. So let's go back to the half-wave rectifier. And this time, so what I would like to remind you was that if the input is a sine wave like this, so that is V in, and our circuit looks like this with an input voltage source and a resistor here, and V out measured between these 2 points. What we saw was that the output waveform is rectified. So for the output waveform, we'll use a different color, blue. We saw that it's 0 until V in is large enough, of one diode drop, to turn on the diode. Then it starts tracking the input with the diode level shift. So the difference between these two is a constant value of VD on, 700, 800 millivolts. And then it turns off again and stays off until the next cycle. All right, so in many applications, this output is not particularly useful. So imagine the charger application. We said we have a charger, so let's say this was a laptop charger that we had before, and we said one side goes to the 110 volts or 220 volts from the wall, and the other side gives us a DC that drives a laptop computer. So we said first we have to reduce that very large voltage of 110 or 220 to something manageable, which we used a transformer for. Then we said somehow we have to go from this type of waveform to this type of waveform, a rectified waveform. So we have got there. We have a rectified waveform. But that rectified waveform can still not be applied to the laptop because it has huge fluctuations. What we are interested in is the constant value. So some constant value here, but this keeps going up and down. It goes up, comes to 0, goes up, comes to 0. So we cannot give that to the laptop or any other electronic device as the power supply. So we have to do something with that. Now, when we studied the internal circuitry of this charger, we said that we will use a filter after this point, to remove all these high frequencies and just extract a DC. What a low-pass filter does is that, right? A low-pass filter rolls off at high frequencies. So if you look at the Fourier series of this waveform, all those frequencies can be suppressed by a low-pass filter, which we would place here, and we just keep the DC value. Well, what does a low-pass filter look like? In the simplest case, it consists of a resistor and a capacitor, a first-order low-pass filter. So maybe we should do that. Maybe we should put a resistor here and a capacitor between these 2 points to filter out these unwanted fluctuations. Well, yes, but what if we just do this? What if we replace this resistor with a capacitor? Just that. It's interesting. Let's try it and see what happens. The circuit doesn't bite. We can always try it with that. And if it doesn't work, sure, we'll go back to our original idea of using a complete low-pass filter after this. All right, so we will construct a new circuit which we call the halfway rectifier with a smoothing capacitor. So that's what it looks like. We have our input, a sinusoid, then we have our diode D1, and instead of the resistor, we use a capacitor. So here's a capacitor, C1. And this is the output voltage that the circuit generates. And what we would like to do is analyze the circuit and understand what this output looks like. Is it constant? Does it fluctuate? Etc. So the best test in this case, again, is a time response. So we assume V in is a sinusoid like before and try to see what V out comes out as. Okay, so let me use red still for the input waveform. So we have our input waveform here. That's V in. And then I would like to plot the output waveform as a function of time. So I will go to blue for the output waveform and start like this. Okay, well, remember last time when I talked about capacitors, just as a quick review, I said to charge a capacitor, we need to push current into it. Right? We need to put positive charge on the top plate to charge this capacitor. And to discharge the capacitor, we need to pull charge out of the plate this way. So if the current keeps going out of the capacitor, the voltage on the capacitor collapses. If the current goes into the capacitor, the voltage across the capacitor rises. So we just have to remember that. Now, let's suppose that V in is 0 right here. Then assume 0 initial condition across the capacitor. So 0 here, the diode is off. So nothing is happening, V out is 0. And again, we are using the constant voltage model provided that the diode is on. The input begins to go up. The output doesn't change because the diode has not turned on yet. So this side is 0, this side keeps going up. When this side reaches 1 diode drop, VD on, D1 turns on. So somewhere around here, when we are at VD on, just like before, the diode turns on. When the diode turns on, we have a battery instead of D1. So when D1 is on, if V in is greater than VD on, then D1 turns on, and the circuit reduces to this. We have the input sinusoid, V in, then we have a battery for the diode. So From now on, I just draw a battery when the diode is on. I will not draw that switch that was a short circuit. So we have VD on here, and then we have the output. So there's a capacitor here, and there's a voltage that we are measuring at the output. How much is V out? Well, simple KVL. This voltage minus this voltage is this voltage, regardless of what we have here. As long as this is an ideal voltage source, and this is an ideal voltage source, they override anything that we place here, except for another ideal voltage source. So regardless of how large or small this capacitor is, the voltage that we measure here is exactly equal to this voltage minus this voltage. That's just KVL. So V out is equal to V in minus VD on. So again, that tracking property that I mentioned earlier holds here as well. Okay, so when the diode turns on, the output begins to track the input with a level shift. So we are here, and we begin to track. So we track all the way to here. So far so good, nothing exciting, nothing that different from the original full half-wave rectifier that did not have a capacitor. All right, so we reach this level, some amount. For example, if the peak value of V in is V0, then the peak value that we measure here is, let me be careful here because I need that space. So the voltage that I get here will be V0 minus VD on. So this voltage, I will draw it over here. Sorry that I'm way out in the Neverland. So V0 minus VD on. That's this voltage, the peak voltage that I measure here. Now, we reach V0 at the input, and now the input starts going down. In the previous case, the output also starts going down. The output still tracks the input. But how about here? Does it happen? All right, well, so here's the situation. We have this diode and a capacitor. This voltage has reached the peak and now is coming down. The question is, what happens to this voltage? Well, there are only three possibilities. This voltage can go up, or it can go down, or it can stay constant. So if we rule out two of them, the third one has to be valid. All right. Well, can this voltage go up after we go this way? No, because for a voltage on a capacitor to increase, we have to push charge into it. Where should that charge come from? Well, that charge can only come this way through the diode, and that happens only if this voltage is higher than this voltage. But that cannot be true, because this voltage keeps going down. So we do not have enough voltage up here to be larger than this to push current through the capacitor. So this voltage cannot go up. Can it go down? Well, for the voltage across a capacitor to go down, what should happen is that charge must come out of the capacitor. If the charge comes out of the capacitor, where does it go? It cannot go that way, that's open, so it has to go this way. But we know that the diode can conduct current only from its anode to its cathode. That was our third principle. So we cannot have a current going this way. So only the third option is valid. Namely, the voltage on the capacitor has to be constant after this point, meaning that the diode turns off after this point. So this is what will happen. So here, D1 is off. And what we have is just an open circuit and the capacitor, but the capacitor holds a voltage on it. And the voltage on the capacitor happens to be V0 minus VD on. So V0 minus VD on. So this is where students often have difficulty. Why did the diode turn off? Well, the best way to think about it is that when we got this to this point, we still have VD on across the diode because it's on. This side is sitting at this value, and this side now wants to come down. Because the capacitor voltage cannot go up and it cannot go down, it stays constant, and if the voltage stays constant and this voltage goes down, the voltage that we have across D1 is now less than VD on. And if it's less than VD on, the diode has to turn off. So from here on, the diode turns off. Again, assuming a constant voltage model. Okay, so that's good. This voltage remains constant forever. So it doesn't matter what happens afterwards, right? We could have negative cycles, positive cycles. This voltage always remains the same. So that's actually very good. That's exactly what we're looking for. We wanted to obtain a DC, a constant value that we can feed to our electronic devices. And the value of that DC happens to be V0, the peak of the input sinusoid, minus 1 diode drop. So that's pretty good. That's something we can use. We don't even need to have this resistor, and we don't need a complete low-pass filter here. All we need is this smoothing capacitor attached to the output of the circuit. All right, this is called a half-wave rectifier with a smoothing capacitor because it carried current for this part and then stopped, and from then on, nothing happened. All right, this is the ideal world and looks pretty good. But there are a few interesting issues that we have to analyze. So, what I would like to look at, one quick note here is the following. So let me change the color of my pen to this color. All right, so reverse voltage across D1. So this D1 turns off at one point, at some point in the operation. So when it's off, it is possibly in reverse bias. If it's in reverse bias, it has a voltage on it. Remember that we can have a voltage in reverse bias. The diode is not conducting really. But if the reverse bias becomes very large, the diode breaks. It breaks down, and it begins to conduct a very large current. So obviously, for these things to happen, to work properly, we want to avoid breaking down the diode at any point in the operation. So that means that we have to find the maximum reverse bias voltage across the diode and make sure that the diode that we select, that we buy, has a reverse breakdown greater than what we experience here. All right, so how much reverse bias do we experience in this diode in the worst case? Well, the diode was turned on here, so that's not a problem. It turned off here. So at this point, we have positive, more positive on this side than on this side, right? This makes a difference. But it's too little, so the diode is off. The diode is off, the diode is off. Now the difference between the input and output is 0. These two have the same voltage at this point in time. Okay, no problem. Now the input voltage keeps going down, whereas the output is constant. This keeps going down, and this is constant. So now we begin to create a reverse bias across the diode. And this keeps going on, going on, going on up to here. At this point, the input is very negative, the output is fixed. And that is the voltage drop that we have across D1. That's the reverse bias that could potentially break down the diode. So this is the maximum reverse voltage across the diode. How much is that? Well, this value we know. This value is on the capacitor, V0 minus VD on. This value is minus V0. You have a sinusoid, plus V0 here, minus V0 here. So that's minus V0. The difference between this value and this value is 2V0 minus VD on. So that's 2V0 minus VD on. So if we buy a diode, its reverse breakdown voltage must be greater than this. For example, if V0 is 20 volts, this is about 40 volts, a little less than 40 volts. So the breakdown voltage of the diode should be 50 volts, 60 volts, something in that range to make sure it does not break down. Okay, so that was one note on that. And now we are ready to move on to some other interesting points. Okay, I would like to raise 2 points before we leave the half-wave rectifier. The first question is, why did we use R1 in the original circuit? So role of R1 in the original circuit. This circuit here. And this question is a question that you need to ask yourself in every circuit that you see. For every circuit, there are a bunch of devices. You have to ask, what is the role of this device? What is the role of this device? What happens if the device is not there? What happens if that device is not there? If you ask these questions and you try to answer them, you will understand the circuit much better. And it's the same thing here. We have only two devices. Can I omit D1 and still have a rectifier? No, we saw a long time ago that diodes are necessary for this type of nonlinear operation. Okay, so D1 is necessary. But how about R1? What is R1 doing here? Well, we can construct a circuit without R1 and see what happens. If it still works, great. We don't need R1, we throw it away. But if it doesn't, then we have to put R1 back in. All right, so without R1, this is what the circuit looks like. We have a diode, and then nothing here. And then this is V out. And that's V in. All right, is there a problem here? Well, yes, there is a fundamental problem here. Let's suppose that for part of the operation, D1 is off. That's necessary for rectification, right? Okay, so if D1 is off, what defines this voltage difference? So if D1 is off, this is what we have. We have an open circuit, and then we have the out. It is incorrect to say that the out is 0. A voltage can be 0 only if we have 0 current through a finite impedance, not infinite impedance. So what do we have here? We don't know. This voltage is not defined. When the switch turns off, we don't know what we have here. So the purpose of this resistor is to make sure that when D1 is off, this voltage is in fact 0, because a 0 current times a 0 resistor, a finite resistor, gives us a 0 voltage. So that's why that resistor has to be there. Now, in other words, there has to be something here. It can be a resistor, it can be a capacitor, or any other component, but we cannot leave it open, because if we leave it open, we don't know what voltage we have here when the diode has turned off. So that's the fundamental reason for this. Okay, the second point is the following. For this circuit, we drew the input-output characteristic, if you remember. So we saw on this board that the input-output characteristic looks like this, 0 up to VD on, and then takes off with the slope of 1. This is for one diode and one resistor. The question is, for the other version, where I have one diode and one capacitor, can I do the same thing? So, can we plot input, output characteristics for the rectifier with capacitors? It would be interesting to try that, right? Just the way we did it for this guy, we can try to do it for this guy as well. Well, the answer to that question is, in general, no. It is very difficult or not very interesting or not very useful or all of the above. Why? Well, before we get tangled up by this complex circuit, we can ask a simpler question. Can we plot, for example, something for just a capacitor? Can I plot I as a function of V for a capacitor? For a resistor, we can do it. It's just a straight line. For a diode, we can do it. It's like this or like that. But for a capacitor, can we do it? Well, the problem is that here, I is equal to C dV over dt. So it is true that the current is a function of the voltage, but it's also a function of time. In particular, it's a function of the derivative of the voltage with respect to time. So how do we reflect this T in our characteristics? That's why things become much more complicated and oftentimes not very useful. So because this circuit has a storage element, a capacitor, in it, its response, its input-output characteristic will be time-dependent, will depend on the shape of the input waveform. It won't be as simple as this characteristic where we just slowly change the input voltage and we observe the output voltage, right? It's much more complicated than this. It depends on how fast the input is changing. So for circuits that have a storage element in them, we generally do not try to create an input-output characteristic or IV characteristic. In some cases it is possible, in some rare cases it's also useful, but for most cases it's not. So we will not do that. In other words, for this rectifier, the primary characteristic of interest is actually the time response, as we have studied here. Very well. We are now ready to go to the full wave rectifier. So we will, okay, actually, sorry, not yet. There's one more idea I have to talk about before we go there. Let me change the color of my pen. All right. So in the next step, we are still on the half-wave rectifier. In the next step, we ask ourselves, what happens if this rectifier drives some sort of load? Like you connect this adapter to your laptop or to your cell phone. So then what happens? Is this waveform just like before, or will there be any changes to it? Will the changes be desirable or undesirable? That's why we have to analyze it. All right, so the next topic that we will study is half-wave rectifier with cap and load. And by load, we mean something other than the capacitor. So here's the situation. I have built this nice little rectifier to generate a DC. So let's say 3 volts or 20 volts. And I'm happy with it. I saw that it goes up and stays constant, so that's great. And then I come along and I connect it to something. Let's say I connect it to a laptop. So we have a sinusoidal input, which is coming from the outlet in the wall, 110 volts or 220 volts. It goes through a transformer, is reduced, then it comes to the circuit here. So that's our sinusoid here. And now, previously we predicted that if we have only a capacitor and nothing else, the output will be constant. But now, it's not exactly that. We have a capacitor, but then we have something else. What does the laptop do in this case? Well, the laptop needs to draw some current to operate, right? So let's say this is 20 volts, and then there's some current here. It could be several amperes of current. Okay, so then what happens? We have to study that carefully. Now, to study that, to analyze the circuit from our basic circuit theory knowledge, we need to have some sort of model for this laptop. Is it a voltage source, a current source, a resistor, a capacitor, inductor, what? What is it? So what we will do is we'll approximate that by a resistor. Even though it may not be a very good approximation, it's still okay for our purposes. So we will do this. We will say here's our input going to a diode, then the capacitor C1, then we model the laptop by a resistor R1. And V out is what we are measuring here, 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 here. So that's all V out. And this is dV1, and this is V in. Okay, that is the circuit that we need to analyze. Is the circuit different from what we saw before? Maybe. What we know are two extremes. If R1 is infinite, R1 is not there, this is what we have. If C1 is 0, C1 is not there, but R1 is there, then this is what we have. Now, it's somewhere in between. We have C1, not 0, we have R1, not infinity, so we have a combination. So we have to see what happens. All right, so this is an interesting circuit. It's not something we have seen before. It takes some patience to analyze it very carefully. So let's go ahead and do that. Well, as usual, we draw the input waveform and then try to look at the circuit in every part of the waveform and see what's going on. Let me draw the input waveform in black for now. So here's the input waveform, V in, and now we begin to draw the output waveform. So for that I will choose a different color, maybe this orange. I don't know if orange shows, hopefully it shows. Okay, so for output, we know that if the input is 0, the output is 0. There's nothing happening in the circuit as before for this case or for this case. So the output is 0. We know that the output does not change until the input is enough to turn on the diode. So when the input has reached one diode, the output turns on. When the diode turns on, the output is pinned to the input, just like this. It doesn't matter whether we have a resistor here or not. We know that this output is exactly equal to the input minus VD on. No question. So the input tracks the output. The output tracks the input. So the output goes and tracks the input all the way to here. So the orange waveform is the output waveform. I will write V out here. All right. Now the question is what happens after that peak? Well, when we did not have the resistor, the voltage stayed constant. Now that we do have the resistor, what happens? Okay. Well, let's say that D1 still turns off past this point. And that's a good assumption in most cases, as we will see. So we will make that assumption for now. Hopefully at some point we can check it to make sure the assumption is correct, but let's make that assumption. So the assumption is that D1 turns off after the peak. So after this peak, the diode turns off. So if the diode turns off, what do we have left? The diode is not here. We have one capacitor, one resistor. The voltage across the capacitor is still as before, 2V0 minus VD on, like here. So this circuit can be simplified to something we are very familiar with. The circuit can be simplified to one capacitor having a voltage on it equal to V0 minus VD on, this voltage here, this voltage here, this voltage, V0 minus VD on, the peak value minus 1 diode drop, and this capacitor is connected to a resistor. So as you remember from basic circuit theory, if you have a capacitor that is charged and a resistor is connected to it, the capacitor voltage, which is the same as the resistor voltage, will decay exponentially. So what we would expect this voltage to do is V out. I will draw it here for now, and then I'll bring it back to the main plane of waveforms. As a function of time, V out goes like this. So that's V out of that little circuit here. This is what we know from basic circuits. Okay, so the same thing should happen here. The diode has turned off. We have a capacitor with that much voltage. We have a resistor. So from here on, it's not a sinusoid anymore. It's a decaying exponential. So it exponentially decays. I deliberately made this decay very slow. We will see why. So that it just gradually is losing charge, the capacitor through the resistor, and gradually coming down. Okay. Now, what is the input doing in the meantime? Well, the input keeps going down, going negative. The diode is still off. That was our assumption. The diode is off, the diode is off, the diode is off. Now, let's look at this point. At this point in time, the output voltage has decayed, the input voltage has come back up, and they happen to be equal. This voltage happens to be equal to this voltage. Does the diode turn on? Not quite. If we use the constant voltage model, we need this much voltage for the diode to turn on. So not yet. Now we have to let the input go up, the output to decay, until the difference between these two in this direction is sufficient to turn on the diode. So when this is sufficiently more positive than this, one diode drop, the diode turns on. So diode turns on right here. So D1 turns on again. So maybe I should write here as well. D1 turns off. Well, I guess I wrote it before, so I don't need that. But anyway, D1 turns off. Okay, D1 turns on again. Now, if D1 turns on again, what does the circuit look like? Here's what we have. We have a voltage source, VD on, a battery, and V in, a sinusoid that's going up, and the capacitor again. The voltage on the capacitor is about input minus VD on. So at that point in time, we have a situation where the input is some amount, we have VD on here, and the voltage on the capacitor happens to be this voltage minus VD on. That's when the diode turns on. So now what happens? Well, again, the output is pinned to the input. So the output continues to track the input. We track the input. Up to what point? Up to the peak. We reach the peak. At the peak, we still have V in minus VD on across the capacitor. And then, once we go past the peak, the diode turns off. So, we have another decay afterwards. In other words, this waveform from here, this waveform from here to here, and from here to here, repeats. We decay, then we charge the capacitor again, then we decay, then we charge the capacitor again, and so on. That is the output waveform of the half-wave rectifier in the presence of a load capacitor and a load resistor. All right. The waveform that is generated here, instead of the constant DC that we produced before, is called a ripple. So this is called ripple. We say we have ripple on the waveform. Ripple is like what you see on the ocean, the waves, small waves. So we have a ripple here. The question is the ripple a good thing or a bad thing? If it's a good thing, we want to make it larger. If it's a bad thing, we want to make it smaller. Well, what this means is that what we thought was a nice constant voltage given to our electronic device is actually not constant. It fluctuates. So that fluctuation is undesirable. In some cases, very undesirable. I'll give you a quick example. Let's suppose that you have some sort of audio device, like an MP3 player or a radio or something. So imagine that you have a charger that is charging a radio. Okay, so you're listening to the radio, and at the same time you have plugged this into the wall, and this is the DC, presumably the DC, this DC. But when it connects to the device, the audio device, because the audio device draws a current, we have ripple on this voltage. So then what happens? You will hear a humming noise in the background of the music that you're listening to. And that humming noise is because the supply voltage that's coming to the device is not constant. It keeps going up and down at a frequency of, for example, 60 hertz in US or 50 hertz in other countries. So that is a problem. The ripple must be minimized. Well, now the question we have to ask ourselves is, how much is this amplitude of ripple? From this peak to this valley, how much have we lost? We have to calculate that. Once we calculate it, we see how it depends on the various parameters of the circuit. And from there, we can decide how we should reduce the amount of ripple, how we should suppress this effect. All right, so how do we calculate the ripple? It looks a little complicated because we have a nonlinear circuit, we have part of a sinusoid, then an exponential decay, and so forth. So it doesn't seem to be straightforward. But we can make some approximations. The approximations are as follows. We know that this circuit is presumably well designed, which means its ripple has to be small. Okay? If the ripple is small, it means that this decay is very slow. It starts from here, it decays very slowly, and touches here, and then again. So for the ripple to be small, the decay has to be very slow, so that we don't lose much charge from this capacitor when the diode turns off. All right, so if the ripple is slow and small, then we can draw two conclusions. Conclusion number one, if the ripple is very slow and small, what happens is that the diode turns off here, and it turns on around here. It turns on very briefly. And that makes sense, because if we didn't take much charge out of this capacitor by the laptop, we don't need to provide much charge to it in the next cycle. So the diode turns on only briefly here, if the ripple is small and slow. So what I can say is that this decay lasts about one period of the input. It starts from here and lasts about, not completely one period, but close to one period. So I will write that down here. That's a very important assumption that we're going to make. So if the ripple is small, then decay lasts about T in. And T in is the period of the input. So for example, it's easier if I show it here. So T in is from peak to peak, one positive peak to the next positive peak. So here's T in, or from one zero crossing to another zero crossing, from here to here, or from here to here, etc. That's T in. So we can say that from here when the diode turns off until the diode turns on again is approximately T in. This is only true if the ripple is small, and the ripple has to be small for this design to be a good design. If the ripple is large, then we'll have lots of humming noise in the audio device example I mentioned, and then it's not a good design. Okay, so if that's the case, we can assume that this decay lasts about T in seconds. If the frequency of this voltage is 50 hertz in other countries, then T in is 20 milliseconds. If it's 60 hertz like in US, then T in is about 16.7 nanoseconds, 16.7 milliseconds, right? So those are the numbers that we can keep in mind. All right, so we made one assumption so far, that the ripple is small, hence the decay is slow, and therefore the time from here to here is approximately equal to T in. All right, now to calculate how much the voltage has fallen from here to here, I need to go back to basic circuits and analyze this type of circuit again. So let's go ahead and do that. So let me add a page. Okay, here's the circuit that we analyzed, assuming the diode has turned off. We have a resistor and a capacitor, and we have R1 and C1. There's a voltage, some voltage here. Let's call it V1, the initial voltage. And I would like to analyze the circuit. Now remember from basic circuits that the response looks like this. Okay, so let me call this V out, but I will write initial voltage on C1 is equal to V1. So V out as a function of time for this very simple circuit is like this. It starts at V1, goes to 0, and we know that this equation is V1 exponent minus T over tau. Okay, so that's what we know when a capacitor discharges through a resistor. Now, we are making an assumption that the discharge, the decay, is very slow. Does that allow us to make an approximation for this waveform? Yes, and this is a very good approximation to remember for your career. Oftentimes, it's very helpful. Okay, so let's suppose that we are observing this waveform for a time duration much less than tau. So for example, tau is 1 second as an extreme case, but we are observing this waveform for only 1 millisecond. So the observation window, the observation time this t, so from 0 to some t, is much less than the time constant. In other words, we are not interested in what happens later. We are only interested in the first, let's say, millisecond, while tau is 10 milliseconds, 100 milliseconds, 1 second, very large. Okay, so if t, the observation window from here to here, is much less than tau, I can approximate this exponential. You remember, exponential of a very small number is 1 plus that small number. So we can say that if t is much less than tau, then v1 x of minus t over tau is approximately equal to v1 1 minus t over tau. And this is not that surprising. The idea here is that if we are interested in only a very small part of this waveform, we can approximate it by a straight line. This is a straight line, so we can approximate it by a straight line. Right? That's what all this says. Okay, good. So in the half-wave rectifier with a capacitor and a resistor connected to the output, if the decay is slow, we can approximate the decay by this waveform. So let's go back there for a second and see what we have seen so far. So what I'm saying is that this decay from here to here, which is in this simple circuit, a capacitor discharging through a resistor because the diode is off, can be approximated by a straight line going down. And that line is given by the initial voltage, whatever we have here, which we know. The voltage we have here is V0 minus VD on, peak minus one diode drop, multiplied by 1 minus T over tau, assuming that this is a very slow decay. The observation time for us is from here to here, approximately T in seconds. The time constant of this discharge is very large, much greater than our observation window. So we can approximate this line, this waveform here, by a straight decay, by a linear decay. So I will just remember that this voltage, the initial voltage, is equal to V0 minus VD on. So let's go back here and write for the half-wave rectifier, we have V out is equal to V0 minus VD on multiplied by 1 minus T over tau. This is the decay behavior during the time the diode is off. Okay, so we approximated that exponential decay by a linear decay. Now what we are really interested in is the amount of decay at the end of that discharge. So we go back here, we are interested in this voltage here. We decayed and decayed and decayed until the diode turned on. So at this point, past this point, we don't decay anymore. So how much is the voltage here if we know the voltage here? So this voltage is V0 minus VD on. We are interested in this voltage. Now, we know the time from here to here. We said that's approximately equal to T in. We said if the ripple is small, then we can say the decay lasts about T in seconds. So we go back here and we replace T with T in. So we say V out at T equals T in is equal to V0 minus VD on 1 minus T in over tau, and this is an approximation. All right, so this is what we have. We had this decay. Remember, we charged up, and then we decayed. And what we have found is the equation for this decay from here, which I'm assuming 0, to here, which I'm assuming approximately t in as a function of time. Okay? And that is the equation that we had, V out. All right, so what I'm really interested in is this height, how much we had at the beginning and how much we have after t in seconds. So we found the voltage at this point in time, that's this. We have the voltage at this time, which is just V0 minus Vd on. If we subtract these two voltages, we find the amplitude of the ripple. So we say ripple amplitude is equal to V out at time equals 0 minus V out at time equals t in. So here we have V0 minus Vd on. Here we have all of this. So the difference between these two is just that. So that's equal to V0 minus Vd on times t in over tau. This is the ripple amplitude. Okay, tau is the time constant of the circuit equal to R1C1. T in is the period of the input. Sometimes we prefer to express it as 1 over F in being the frequency of the input. So sometimes we write this as V0 minus Vd on divided by divided by R1 C1 F in. F in is the input frequency, 60 Hertz in US, 50 Hertz in other countries for the line voltage. So this is a simple compact equation for the amplitude of ripple that we get here. We can see that if C1 is smaller and smaller, the ripple becomes larger and larger. Why? Well, it makes sense because if the capacitor is small, the decay is really fast, faster and faster. So the ripple becomes larger. We are here, we decay down here. Of course, so long as the approximation of slow decay holds, this equation also holds. This equation also says that if R1 is small, the ripple is large. Why? Well, if R1 is small, again, the decay is faster. And that means that if we connect a heavier load, by heavy we mean a load that draws a lot of current, then the ripple will be larger. So if the charger, like this charger, drives a, let's say, a simple Bluetooth device, which doesn't draw much current, the ripple might be only 10 millivolts. But if the same charger has to drive something with a lot more current, let's say a laptop or some other device, then the ripple will be larger. And that's what this equation tells us. Okay, so it's a nice little equation that is very useful in trying to decide the values that we need here. This is usually given, but at least these two values, for a certain amount of ripple at the output of the half-wave rectifier. All right. Well, looks like we did not get a chance to look at the full-wave rectifier. And at this point, our time is up. So I will see you next time when we talk about the full-wave rectifier and we repeat all of these analyses for it. I will see you next time.